This is your presenter, Asloob Mudassar, and I am presenting slide number 16D of the course on atomic and molecular physics. In the today's lecture, I shall be discussing Auger effect and Auger electron. This is the fourth lecture of the series on X-ray spectra. The Auger effect may also be referred to as inner photo effect. Inner electrons are removed either by electron bombardment or by optical means. Not all atoms return to the ground state by emitting X-rays. Quantum yield for X-ray emission is less than 1, which is defined by eta, which is the quantum yield for an X-ray emission, is equal to the number of X-ray emitting atoms divided by the number of ionized atoms. That is how many ionized atoms you have and how many out of these ionized atoms emit the X-rays. Because not all ionized atoms will emit X-rays. Some of them will emit X-rays, but some of them will not emit X-rays. Because when they will not emit X-rays, then for such atoms, there will be a non-radiative decay. So eta is actually the number of X-ray emitting atoms divided by the number of ionized atoms. That is the number of ionized atoms in the K shell, number of ionized atoms in the L shell, number of ionized atoms in the M shell, and so on. So in the denominator, we have the total number of ionized atoms at a time. And out of these, how many are emitting the X-rays? That is referred to as the quantum yield. And of course, obviously, eta has a value which is less than 1. Because all the ionized atoms will not radiate. Some of them will relax through the non-radiative process. And the relaxation through a non-radiative process will be referred to as the Auger effect. Eta increases with nuclear charge Z. So for the heavier atoms, the value of eta will be relatively larger. That is with the heavy atoms. The non-radiative return to the ground state is accomplished by the Auger effect. So you see that when we talk about the Auger effect, it means that we talk about the non-radiative decay to the ground state of the ionized atoms. So if you have ionized a sample of atoms, some of those atoms will be emitting X-rays, but some of ionized atoms will be relaxing to the ground state through a process which we refer to as the non-radiative return. That is, no X-rays will be emitted in that process. And this is accomplished through a process known as the Auger effect. For example, look at the plot of the value of eta, that is the quantum, which is the quantum yield. So eta is plotted along the vertical axis. The maximum value of eta could be equal to 1. And on the horizontal axis, I am plotting the nuclear charge or the atomic charge Z. And you will see that when Z increases, the value of eta increases. And it gets a value of 0.5 at a value nearly at 40 value of at Z is equal to 40. But if you further take a sample with Z greater than 40 and keep on taking the samples up to, for example, 80, you will notice that the value of quantum yield will keep on increasing. In some region it is a linear, but in some region it is non-linear. However, we shall notice one thing, that the quantum yield will increase with the value of Z. Suppose that a K electron is ionized and an L electron fills a hole in the K shell. So you see that when you ionize K electrons in an atom, through, and you know that the ionization is done by another electron, which you accelerate through some potential difference, and that electron will be bombarded on the anode, and in the anode sample, the electrons will be the k electrons of that sample will be removed. So such a sample is called that the k electron has been ionized. So when the k electron is ionized, then of course a vacancy of hole is created. A vacancy of electron is created in the K shell, which we refer to as the hole in the K shell. And that hole may be filled by surrounding by the electrons from the surrounding shell. For example, from the L shell, from the M shell, from the N shell, from the O shell, and so on. So here I am talking about the L shell. That an L electron fills a hole in the K shell. The energy released is used to remove a second L electron from the L shell. So you see that this L electron. So let's start from the beginning. We have an atom with K electron removed. That is, there is a hole in the K shell. So an L electron jumps from the L shell to the K shell to fill the valency, to fill the vacancy. So in that process, the binding energy, which is the difference of the energy of the electron in the L shell and the difference of energy of the electron in the K shell, that energy is released in the form of quanta of light. But that quanta of light is not released because that quanta of light is absorbed by another L electron, and that L electron is ionized. So you see that we shall not observe any light emission in this process. So this process will be referred to as the non-radiative decay. And the electron the L electron which is removed from the atom is referred to as the Auger electron. So let me read the statement so that it becomes clear. The energy released is used to remove a second L electron from the L shell. That is, L shell loses two electrons. One from when the electron from the L shell jumps to the K shell. So there is a one loss of L electron. Other when that energy, that is when the electron jumps from L to the K shell, the difference of energy, the difference of the binding energy will appear as the quanta of light, and that quanta of light is absorbed by another L electron, and that L electron is removed from the atom. So I have written that L goes to infinity. It means that there are two electrons in the L shell which we have removed. One electron has jumped to the K shell to fill the vacancy, and as a result, the quanta of light which is emitted due to the difference of binding energies of the electron in the L shell and the electron in the K shell, that quanta of light is absorbed by another L electron, and that L electron is removed from the atom or ionized. So a holes in the L shell are filled is created, and the two holes in the L shell are filled by electrons from the other higher shells, that is from the M shell and so on. The one electron of the L shells, the one of the L electrons that leaves the atom, that is the L electron which has been ionized, is called the Auger electron. When a K electron is ionized, there may be two possibilities. So you see that when you ionize a K electron, how that vacancy is filled, there may be two possibilities of filling that vacancy. One is the possibility that I have discussed above in case of the Auger electron. So let's discuss the complete picture. That what are the possibilities that an K electron vacancy is completed or filled. This is indicated in this diagram. First of all, I speak about the Auger electron. So you see that this is the nucleus, and there is a green shell which we call the LK shell, and there is another shell which is L shell shown in red. So when a K electron is removed by the bombardment of an outer electron onto the anode, and the anode in the anode, the k electron in an atom, the k electron is removed. So a vacancy of an electron is created in the k shell, or we can say that a hole is created in the k shell. So here you can see on the right that an electron shown in the red dot is moving towards the k shell. So this electron from the L shell will complete the vacancy of the k electron. And when this electron jumps from the L shell to the K shell, then of course a quanta of light is generated. That quanta of light is absorbed by another L electron, and that electron, that is the second L electron, which is shown by an arrow, is removed out of the atom, or the atom with respect to the L shell is ionized. That electron, which is that L electron which is removed, is called the Auger electron. So this is one picture that the K vacancy is filled. The second picture is that the electron, you see that another electron, an electron from the L shell jumps to fill the vacancy in the K shell, as shown on the left hand side of this picture, and a quanta of light is created. This quanta of light comes out of the atom as the X-ray emission. So what happens? Either you detect X-rays or you detect nothing. So the process of in which the Auger effect is generated, or the Auger electron is generated, this is the non-radiative decay. That is no quanta of light is emitted in the process of Auger effect. Whereas when a simple vacancy is filled by an L electrons, an X-ray is an X-ray due to the difference in binding energies of the difference in an electron in the L shell and an electron in the K shell will be generated. That quanta of light comes out of the atom in the form of an X-ray emission. So what we have defined over here, in terms of the quantum yield, number of X-ray emitting atoms divided by the number of KLM ionized atoms. And you know that in the numerator we have X-ray emitting atoms. And you know that its value is smaller than the values in the denominator. That's why it has a value less than 1. So the number of X-ray emissions from such atoms is smaller in comparison with the number of ionized atoms. And you know that those ionized atoms is the total number of ionized atoms, out of which some atoms will be emitting X-rays, and out of these ionized atoms, some atoms will be undergoing through the process of Auger effect. So the ionized atoms have two roles. One is that they emit the X-rays, and the second is that they undergo through a process of Auger effect, and an Auger electron will be generated. So you see that eta is defined as the number of X-ray emissions divided by the X-ray emissions plus the Auger effect, plus the electrons emitted in the Auger effect. Now I am going to present in statements what I have said about the Auger electron and about the emission of X-rays. Number one, an L electron fills the vacancy of K holes. The binding energy is released in the form of a photon or in the form of a quanta of light, which removes another L electron because that quanta of light is absorbed by another L electron of the atom from the atom, resulting in non-radiative decay. That is, no emission of X-ray takes place because the X-ray which was to be emitted was absorbed by another L electron, which we call as the Auger electron, and that electron is ionized or removed from the atom. And in that process, such a process may be referred to as a non-radiative decay process. No X-ray emission takes place in this case. The second option is that an electron or an electron from a higher shell fills the K hole. vacancy, resulting in the emission of an X-ray photon, as shown on the left-hand side of this process. That is, this is the emission of X-rays. Now let's talk more about the Auger electron. The kinetic energy of the Auger electron is given by. So you see that here I am talking about the kinetic energy. So you have removed an electron over here, that is the L electron, which is called the Auger electron. But you know that when an electron jumps from the L shell to fill the vacancy in the K shell, a quanta of light is generated. That quanta of light will give energy to another L electron and will remove that electron. But you know that the quanta of light which is generated might have more energy than the energy required to ionize the another L electron to act as the Auger electron. And the difference of that energy will appear as the kinetic energy of the Auger electron. So the kinetic energy of the Auger electron is equal to E kinetic is equal to H nu K alpha. And you know that when we talk about K alpha, it means that I am talking about the transition from the L level to the K level. That is, an electron from the L shell is moving to the K shell to fill the vacancy, and a quantum of light which is h nu kappa alpha is generated. And you know that this h nu kappa alpha will give some energy, will provide an energy equal to the binding energy of another L electron. So El is actually the binding energy of another electron, which this quanta of light gives an energy, and that El energy, that L electron in the shell is ionized, and this is the binding energy. El is the binding energy of that L electron, which will act as the Auger electron. Now you see that due to this difference, some energy will be given as El, but rest of the energy with the H nu kappa alpha will appear as the kinetic energy. So H nu kappa alpha can be written as Ek, which is the binding energy of the electron in the K shell, minus the binding energy of the electron in the L shell, because this difference of energy will appear as the quanta of light, which is H nu K alpha. So H nu K alpha is equal to E K minus E alpha. So we are substituting H nu K alpha by E K minus E L, and then minus E L, I have E K minus 2 E L. So this is the difference of energies that the Auger electron will acquire as the kinetic energy. El and Ek are the binding energies of the electron in the L and K shells respectively. So simply is that when the first electron jumps to the K shell, due to the difference of binding energies between the electron in the L shell and the electron in the K shell, a quanta of light is generated. That quanta of light is much stronger in energy than the energy required to remove the second L electron. So the second L electron is removed as the Auger electron, and the difference will appear as the kinetic energy of that electron, which I have stated mathematically in equation number 13. Now I am going to present a numerical example in which I am going to analyze the different sets of energies, giving different examples. Here you see that I am talking about the silver atom, Ag, is bombarded with K alpha radiation. This K alpha radiation is generated from the tungsten anode, because in the tungsten anode we bombarded the tungsten anode with some energetic electrons, and those electrons causes the tungsten anode to generate the K alpha radiation. So K alpha is the radiation generated by the tungsten anode, and this K alpha is absorbed by the silver atom. So let me read the statement again. Silver atom is bombarded with this K alpha radiation, and this K alpha radiation was generated from the tungsten anode, and this K alpha has an energy equal to 59.1 kilo electron volt. You see that here I have represent the energy of the K alpha not in terms of the joule, but in terms of the unit of energy that is used to specify the energy of electron. So K alpha has an energy equal to 59.1 kilo electron volt, and the following energies are observed. You see that in this process we have observed an energy which is equal to 50.8 kilo electron volt. So let's account to how we can justify this energy which is 55.8 kilo electron volt. So you know that we have the okay, when this energy which is 59.1 kilo electron volt, which is the energy of the K alpha radiation, when this radiation is bombarded on the silver atom, the silver atom is ionized. So photoelectrons from the L shell of the silver atom is ionized, for example, in this case, and El, that is the ionization energy of the L electron from the silver atom, requires this much energy, 3.34 kilo electron volt. So what is the difference now? Because you bombarded the silver atom with this energy, 59.1 kilo electron volt with K alpha radiation, and the L electron is ionized from the silver atom, for which the ionization energy required is 3.34 kilo electron. Where is the difference of energy? The difference of energy between the K alpha radiation, which is 59.1 kilo electron volt, and the energy required to ionize the L electron from the silver atom is minus 3.34 kilo electron volt. The difference of energy is 55.76, which may be approximated as 55.8 kilo electron volt. So that is the incident photon, that is the incident K alpha radiation with energy 59.1 kilo electron volt ionized the L electron with an energy 3.34 kilo electron volt, and the difference of energy, which is 55.8 kilo electron volt, which we have calculated in this section, will appear as the kinetic energy of that L electron ionized from the silver atom. So you see that this is how we have explained this energy 55.8 kilo electron volt. That is what we have detected this as the kinetic energy of the electron from generated from this process. And we found that this is not any general electron, but this was the L electron ionized with an energy of 3.34 kilo electron volt, and the difference indicates 55.8 kilo electron volt, which we have experimentally observed this energy of electron. So it means that electron was the L electron of the silver atom ionized with an energy of 3.34 kilo electron volt. Okay, now let's account another energy, which is 33.8 kilo electron volt. How we can explain this energy? This energy was also measured in the process. Now the incident photon, which is 59.1 kilo electron volt K alpha radiation, ionized the K electron. In the previous example, we explained the energy using the L electron, because L electron was ionized in this case, and here we are assuming that the K electron was ionized from the silver atom, and Ek ionized for the silver atom is equal to 25.4 kilo electron volt. So this is 25.4 kilo electron volt is the energy that was required to remove a K electron from the silver atom. And the difference of energy, that is the difference of energy between the 59.1 and 25.4 is 33.7 kilo electron volt, which appears as the kinetic energy of the photoelectron. So you see that in the above process, in the bombardment of K alpha radiation on the silver atom, if we observe this energy, which is 33 K electron volt, it means that this is the energy and can be explained only when we assume that a k electron from the silver atom was ionized, which required an energy of 25.4 kilo electron volt, and the difference of energy between 59.1 and 25.4 was equal to 33.7 kilo electron volt, which explained that the emitted electron has this much energy, which we measured experimentally, and from that one we noticed that that electron was the k electron from the silver atom, because for that k electron the energy required to ionize was 25.4 kilo electron volt. So in this way we can justify 33.8 keV as the kinetic energy of the electron emitted in the process. Now let's explain this energy, which is 21.3 kilo electron volt. How we can explain this energy? You see that here I am talking about the energy difference between two processes. One is the Ek beta for the silver atom minus the ionization energy for the L atom. You know that when we talk about K beta for the silver atom, it means that it is the transition from the M electron to the L electron, to the K shell. So when an M electron moves to the K shell, then the light or the quantum of energy that is emitted is called the K beta radiation. So here we are assuming that an M electron from the silver atom and an M electron from the M shell of the silver atom moved to the K shell to fill the vacancy in the K shell. And then of course this energy is referred to as the Ek beta of the silver atom, and minus we have because this energy is used up in ionizing the L electron from the silver atom. So I have shown the difference of these two, and the value of Ek beta, which we measure in another experiment, its value is 24.9 kilo electron volt. That is the radiation K beta, which is the radiation due to the quanta of light emitted as a difference of binding energies between an M electron and the K electron, which we refer to as the K beta radiation. It has an energy of 24.9 kilo electron, and this energy ionized an L electron of the silver atom, which requires an energy of 3.34 kilo electron volt. The difference of these two energies is 21.56 kilo electron volt. So it means that if we measure the energy of an electron to be equal to 21.56 kilo electron volt, it means that this was the electron that was an L electron ionized from the silver atom, and this L electron has gained a kinetic energy because this electron was that is the L electron from the silver atom was ionized when it was provided this energy of the K beta radiation, and the value of K beta radiation was 24.9 kilo electron volt measured in another experiment. So you see that the difference of these two will appear as a 21.56 kilo electron volt. So when we measure this energy, kinetic energy of the electron, we shall assume that this was actually the L electron ionized from the L shell of the silver atom with a radiation of K beta generated from the silver atom. So let me explain this one in terms of the statement. An M electron moved to the K shell to fill the whole vacancy, and a difference of a binding energy appeared as light quanta, which removed the L electron, and the difference 21.56 kilo electron volt appeared as the kinetic energy of that L electron. So the next energy value is 18.6 kilo electron volt, which we have also measured. Now we have to justify this energy, which is 18.6 kilo electron volt. So you see that in order to justify this one, we are assuming a difference between the energy of the radiations, which is K alpha radiation, and the energy which is required to ionize the L electron. So the K alpha radiation from the silver atom measured in another experimental setup was found to be 22.1 kilo electron volt, and the energy required to ionize an L electron from the silver atom is 3.34 kilo electron volt. So when this K alpha radiation was encountered with the L electron of the L shell, then this L electron is ionized, and the difference of the energy between them, that is the difference of 22.1 and 3.34 kilo electron volt, will appear as 18.76 kilo electron volt as the kinetic energy of that electron. And you know that, of course, we have removed the L electron. One electron from the L shell moved to fill the K vacancy, to fill the vacancy of the K electron, and K alpha light is generated. That K alpha light ionized another L electron. So you see that in this process there is a movement of two electrons. One of the L electron moved to the K shell, and the second condition is that the K alpha radiations removed the second L electron from the atom. So this L electron is actually the Auger electron, and this Auger electron will acquire an energy of 18.76 kilo electron volt. So let me read this statement. An L electron moved to K shell to fill the whole vacancy, and a difference of binding energies which is equal to 22.1 kilo electron volt ionized an L electron with ionization energy of 3.34 kilo electron volt, and the difference of energy, which is 18.76 kilo electron volt, will appear as the kinetic energy of that Auger electron, of that L electron, which is the Auger electron in this case. So you see that in the today's lecture, I have explained the Auger effect in detail, giving some examples that I can justify the energy emissions of the electrons. So you see that these were the energies of the electrons. 55.8 kilo electron volt was the kinetic energy of the electron. 33.8 kilo electron volt was the kinetic energy of another electron released in the process. Then 21.3 kilo electron was the energy of another electron released in the process. Then 18.6 kilo electron was the kinetic energy of another electron released in the process. So you see that we have discussed four electrons with the different values of kinetic energies released in the process when K alpha radiation from the anode was incident on the silver atom. And we have justified that how we can justify these four different kinetic energies of the electrons. Now you see that the lecture is continued. This is the fourth lecture of the series, and still the lecture is continued. So this is the end of slide number 16D.